All right.
Thank you, Grant. That was great.
Cool. Thank you. Yeah. Thank you.
uh, anybody else want to go next? Troy or Robert? What do you want to? Which you want to go, Troy?
Yeah, I can go.
Okay.
I did put these on Victor, but I'm thinking there's a proj issue because it wouldn't run it. So I'm actually showing them. Yeah, I'm showing them from my computer.
Okay, that's good to know. Have you talked to Sam about that?
No, yeah, I actually just found out just before class because I went to go run through them all because some of the maps take a little bit to make and they wouldn't do it. So I just jumped back to my desktop to do it.
Oh, interesting. Okay. Okay. Well, it's good to know. We'll try to figure that out. Anyway, go ahead.
Yeah, I have two different notebooks I'm going to show today. One is on magnetic data processing and looking at really terrestrial magnetic data, so walking with a magnetometer, and then doing some of the processing on the data and then visualizing that. And then I'm also going to present my gravity one as well, which does a number of reductions to the observed gravity from the field, and then also visualizes some of that data as well. So at the beginning, I have just a little bit of text in here, just talking about what the notebook does, some of the reductions that are performed, and then also a little bit of the metadata. I don't think they absolutely have to be fixed to run this code, but at least it gives you an idea of the data that I'm using. Of course, going in and downloading a bunch of libraries and modules to use in the program. And I have a whole slew of processing functions that it walks through. And these are just loading the functions in, and I call them later on. So there's an import one, which really, I didn't need one, but I decided to put one in there because I use it a lot. A reprojection function, and this utilizes proj. And you pass it a few arguments for your basically your zone and to go from UTM to lat long and vice versa. And there's a inverse key that I implement for that. And then I detrend the total magnetic data from the observed data, which is pulled from the NOAA website using an API key. And it uses like an average location in my field. I would imagine for much larger surveys, you would want to be a bit more specific, but for smaller surveys, you can get away with that. And then I noticed also that with the magnetometer that I'm using, it causes spikes in the data occasionally, depending on the orientation of the magnetometer relative to the magnetic field of the Earth. So it can sort of drops out and creates these very, very low values. So I went through and manually picked what values I wanted to keep. Then normalize the data, so it kind of pulls everything down to zero by removing the mean. And then there's a rolling average filter that works on a time array. And it takes basically it's set up in seconds. So I figure about every 3 seconds I'm walking a meter. So it's pulling every 3 seconds. It pulls out 100 points and takes the mean of that window and replaces it and moves over one. And then I start to get into here with the visualization of things. In both of these, you will see codes for UTM coordinates for visualization as well as lat long because I'm preparing future Troy for other things. And for these, they have scale bars, they have grid lines, they have the actual map that it pulls in from Google Earth. It's a tile, so it makes a pretty nice field map at the end of it. And further on, I have a multiple different profile plots. And again, this is like a living document. So I'm constantly changing things. I'm constantly adding and taking away and refining. Like Grant said, when you start out, it's kind of a mess, and then you start to get a process to it. So almost all of my functions are set up for east, west, north, south lines, meaning that, when I do a magnetic survey, you can go in either direction. You can go in any direction you want, but for the east, west, south lines, it's just basically I tell it it's going east, west, or north, south, and it automatically makes that plot relative to the direction. Same with the rolling average profiles. And then I have another one here where I have a topographic profile with a map and inset that has a location of a box that's inside the graph as well. So just walking through it. loading the data in. And again, if you're going to use maybe a different data set, this may have to change depending on what your data is, but I'm basically pulling in certain columns of my data and renaming them just for simplicity. Then reprojecting those coordinates. So the magnetometer I use gives me a latitude and longitude, but I find it a lot nicer to visualize things in easting and northings, especially for smaller areas.
So wait a minute,
And
Troy, is that the cell that didn't work in
yeah,
Antarctica?
when I ran it, this thing it crapped out. It threw an error.
Really?
So
Okay.
yeah,
Is that
and I know
different?
there's an easier way to write these. They use the EPGS numbers. I might have switched those, but I like to have that sort of added control of like knowing exactly. You have to go look those numbers up, and maybe you get the projection wrong or something. With this
Yeah.
particular setup, I think it's a little bit more straightforward on what you have to add in. Um, and then from there, I just really start visualizing step by step what these things look like. So this is just the raw data, just like what's it look like. And immediately you can see some of those big spikes I was talking about where the magnetometer just dropped out. And if I added those in or kept those with the data as I was processing it, it would blow up some of the data in certain places. So you really want to get rid of those as best you can. And talking with people, I found that doing it manually was probably the easiest way to go. So that's what I ended up doing. And then here detrended it. So that just pulled that information from that NOAA website. And that's the total magnetic field of that area on that given day. And I removed that from the data set. You can see it immediately started pulling that right down to 0, which is kind of what you want when you're looking at these anomalies. You want to be able to see what they are relative to 0. So you can see the actual amplitude of them. And I have steps in here along the way where you're saving the data as you go. You're saving the profiles as you go for every step. Might not be needed, but it's nice to have that stuff. And then here is I look at the detrended data, the detrended data, and I want to say, okay, what's my max and what's my min and then I look at the second lowest values as well and second highest to see if there's a major difference. Like does it go from 8,000 down to 2,000? Well, I don't know if I want to keep the 8,000 point. And for simplicity, I don't even know if those were the actual values that I used for this line because I was playing with this earlier. But as you can see, it pulled out pretty much anything above 4,000 on both sides. And I think that sounded right because this here's 4,000 and that's why I kept it. Yeah. And then again, saving the data and the profile, which may not be necessary, but it could be helpful. Then here I normalize the mag, and I did include some print statements inside my functions so I know when they're done, because some of them do take a little bit. In fact, detraining the profile can take a few minutes. So I like to know when it's done instead of just kind of blankly staring at my computer screen waiting for it. And then after that, I plotted all those data up. So taking this is the despike detrended data again, that same sort of visualize it, see what it's doing. Then after that, I perform a rolling average. And what this does is I created a time array that it then samples based on that time and how much time I tell it to, which is 3 seconds. And above in my code, it actually takes 3 and turns it into milliseconds. And then it kind of skips that window or skips that amount of time and then pulls out 100 samples after it. And then, like I said, it takes the mean of that, and then that replaces the point. It moves out over and continues to do that for that 100 points. Then it skips to the next 3 seconds and does that. And it really smooths out that signal, but it also reduces a lot of those high amplitude noise that you're seeing, which can make life really difficult to interpret what's going on. Looking at this graph, you can see, these peaks here, and if you can draw a line through here, you might be able to see that if you're really good at it. But coming down here, it really makes it a lot more apparent that, hey, there's an anomaly right in this area. Maybe another one over here and another one over here. Looking at the graph above it, it's not as straightforward. Again, saving these profiles as I go along, saving the data as I go along. And then I get into sort of visualizing the field itself and making these data profiles relative to a position in the field, because it's a big deal. Like, okay, how do I correlate this to the geography? So what I do is I pull in an outline of the feature that I've been researching lately, which is Table Butte in Idaho. And then I pull in all the data that I have just so I can show you the field map that I made of all my clipped clean lines. And this code, you can adjust the zoom on it. So if you lower number, it has like lower resolution, higher number has a higher resolution, but after a while, it's about 18. Once you get there, it doesn't really ever make the map. I think you're just getting too high resolution. It's not really pulling it in. So the next one is a map edge buffer, and that's just how much you want outside of your mapped area. And what I used was basically my longest line. I used the endpoints and then the buffers added to those. And here you have a few different options of the kind of background you want. I like to actually be able to see the geography of the areas, so I stick with the satellite view. And again, this is pulling this off of Google Earth. I also implement the same code in my gravity code. It's just really nice to be able to, see this. I can open up Google Earth and compare it and be like, okay, I see what's going on. And I mean, you can get a grid and set up elevation model on it or something to do a similar thing. But even at that, it can be difficult while you're out in the field to actually visualize where you were at in the field with a map like that. With this, I can say, okay, I know I remember seeing that little cinder cone there when I stopped. So I know that I may have to go further, or maybe I can do a line, down on this side or something. It's just really easy for a first cut field map when you're actually out in the field. Again, I had to write the code for the scale bar as well as the grid lines on this because CartoPy, which is the package I'm using to make this map, doesn't actually have grids for UTM, which I thought was kind of weird. So I had to create that. And then going down, I created an inset map for like my final profile that can correlate the profile, the magnetic profile, the topographic profile, as well as where these things are in the field itself. And this basically utilizes the same code that I used for this map, just on a smaller scale. And that's the output of it. Again, I do have some inputs in here where I make things a little bit easier for like saving purposes. So I have an input for a line, so I know like what line it belonged to or whatnot. But more or less the same inputs. You can see the comments aren't there because I really tried to comment a lot of the things that mattered, but I didn't do it over and over again. It's kind of redundant. And then again, I print out importing the topography for the next profile. And here I got it in feet, so I had to convert it to meters. So it matched up, added a new column for that, printed it out just to make sure it was doing what it was supposed to be doing. Again, reprojecting it so I can have my northings because I got it in lat long. And then comes sort of that final profile I was talking about that incorporates the topographic profile with a magnetic profile and then a location map. And in the end, it kind of looks like this. And I have this little box too that I've created that I can outline, the more prominent features. Would like to fine tune this code. This part of it's only like a few weeks old maybe, so I haven't got to play with it more. But I really like the way it came out. You can see this red square matches the place in the field, your topographic profile beyond the butte, and then you have the magnetic profile, so you can line those up to where they are in the field. And then of course saving the profile. So these are the kind of things that you really want for an article, or even just researching, trying to figure out what's going on in the region. And then jumping over to from magnetics to gravity, did pretty much the same thing for gravity. What this does is it walks through a series of corrections to solve for the free air gravity anomaly as well as the Bouguer gravity anomaly. And so it does a drift correction, which basically removes the instrument drift from the magnetometer as it heats up, cools down. It changes throughout the day. So you want to make sure that you're taking into account for all that shifting of those values throughout the day and from day to day or from year to year. Then the theoretical gravity, it accounts for basically the change in latitude, as well as the shape of the Earth. And then you have your atmospheric correction that accounts for the change in density of air above the place that you're sampling. And then the free air gravity correction corrects for elevation difference, and the Bouguer gravity correction accounts for the mass under the point relative to some base station. So there's, if you have an elevation difference, there's a mass associated with that. And it's the Bouguer slab. You sort of remove that to bring everything down to the same level. Outline here with just different formulas on how to calculate each one of these. And then again, I go into the metadata. Some of these things were not, in fact, my drift code in this notebook has not been tested. I just want to say that because and the initial data that I was using, I did it a different way. I feel like I did check it to see if it was working, but I can't say that for certain because it's been a little while. Again, the importing the modules, importing the data, and then you start with the processing functions. These are all pretty much written out. I'm not using many packages other than like really for the data, like NumPy and Pandas. It's about it. So this was the drift correction that I was talking about. And I did try to comment as much as I could for all these things as I'm stepping through them. That way, if you find another thing that you can use it for, especially like the visualization codes, you can tweak those at your will. And stepping through these, implementing the formula here with the latitude is the latitude of your station, and I'm using it relative to my most northern station. So all things created equal, the most northern point is going to have the highest gravity because you get gravity increases towards the poles. Here with the atmospheric correction, I'm using the elevation of my base station. So it's the difference in those two is the elevation that's included in this calculation for each base station or each station gravity station to solve for the correction. And then the free air correction is I need to rewrite that. I see that. Same thing. I'm using the latitude of the station and then the height difference relative to the base station. And then the Bouguer correction is basically just that. You're solving for this density of this slab based on the height difference between the most northern station in the field and your station that you're wanting to calculate it for, which should be further south, obviously, in this case. And then going forward, back to the visualization of everything, because that's the one thing we want to do is be able to see what's going on with our data. And I just pull in a lot of these very similar codes that were from the other one, maybe tweaked a little bit just depending on the data that I'm looking at, obviously. And then here I import my data, which this was just a straight CSV. There was no need to create new columns or rename anything. I was able to use what I had. And then again, I imported the similar outline data that I had for my MAG one because it's the same study area. And then, like I said, I'm taking my gravity, the northing relative. Well, for this one, it was really just to see how well I'm I do this. So I found the most northern station by finding the index of that value and then turning that index into the actual value so then I could call the variable max northing in my code. So then that way I can use that to calculate the northing difference between that and the other points, which is what this next cell does. And then again, the elevation as well using that same variable, but it basically the same thing, just now looking at the max northing elevation versus the max northing. And then here you have to put in a few inputs for the rest of the codes that are all pretty much done in one cell. So it's the latitude of the base, and in that case, it was the latitude of the max northing and the height of the max northing and the corrected gravity base of the max northing. And then all my other data that's involved in this, so the latitude and the longitude of my gravity stations, as well as their easting and northings, then the elevation and the gravity, because I am making multiple images using both lat and long and elevate and easting and northing. So I have like a lat long and UTM version of each one. And then again, the elevation or the height difference was basically just the elevation of the base station minus the elevation of my the other gravity stations, and the same goes for the latitude. And then here is the major cells that from this whole, all the functions that I've created or more, basically done in 2 different blocks. So I do the theoretical correction, which I feed the latitude and the base, because that's all it requires. And then I create a new column for that. Same with the atmospheric correction, the free air correction, and the Bouguer correction. I feed these guys the variables that I've given them. They go into the codes. They spit out, a list of answers, and then I create a new column in my data frame for all those. And then at the end, I calculate the free air gravity anomaly and the Bouguer gravity anomaly, given the corrections from above. And then I create new columns for those as well. And then afterwards, of course, save that data, because that's really the end goal of all of that, is to get this data set. And then after that, of course, it's visualizing it. What do these things look like? What are we seeing in the field? So the first one was all relative to the distance to the north. So these were more sort of first cut images. But after I got a little bit better at understanding what I was doing here, and I go through for each one, I go through for the elevation difference and the drift corrected gravity, free air anomaly, all relative to the most northern point. And you can see here it's distance north in the bottom. And then getting into the UTM and the lat long, what I did is to plot these sort of like an east-west line and a southwest line to see what was going on over the entire area individually in each direction. I cut out data points associated with each of those lines. And I should mention that kind of skipped over at the very beginning up here, something that I did do that you don't want to include your other base stations where you're calibrating the day-to-day gravity meter. Like these are like landmarks that are put there by like USGS, or places that don't change, that are away from traffic and places that can cause interference in the gravity meter. I removed all those readings from the initial data set, and then basically re-indexed everything so I could start with a fresh index, and I dropped the old one. And then using that data that I've removed all those base stations from, I then created 2 copies, and that's actually all the data that was done above was also a copy of the final output, just in case I ended up deciding to change something. I don't want to change my final output data. So here I just kind of cut out an east-west and north-south line. There's probably a prettier way to do that, but it worked. And then I was able to make east-west, north-south profiles of the data points I was seeing in here. And I kind of stepped through these, adding to these graphs, and I kind of just kept everything. So like it was for other people as well, that if, there's something that works for you, I've tried to keep it so you could use it and maybe your research. Kind of now that this is kind of what I mean, where up here I was looking at the north-south lines. I was like, well, that's all well and good, but I don't really know what those points are. I don't know what they correlate to or how I can link those to the geography. And so I went through and I added in an annotation for each one of these points, which made it a lot nicer to like be able to look at my map and say, okay, that's that point, or that's that point. And again, saving all this stuff. And some of this is a bit redundant, but it's nice to have all this stuff just in case. Same thing for the east-west line, added those annotations in and saved it. And then this is very similar to the previous code where I made a UTM field map. I don't think I included the lat long one in this. And it basically is very similar to what you saw in the last one, but my gravity survey went a bit further north and a bit further south than my magnetic survey did, so the map's quite a bit bigger. But I'm able to correlate what I'm seeing on my map to the points that are actually in the field, which is nice. And then even at this sort of a first cut, making this map, you can see where you've got, like what points did I get? Where do I need to get more points at, or more gravity readings from? What can tell a better story? So it's always nice to be able to see your data pretty quickly, especially in the field. And then, adding to this field map, I also wanted to see, and I found out just like a day ago too, that I can add the next plot I'm going to show you, I can add it to this plot. And I did it. I took it back out because I wanted to be able to show you just the plot by itself. But the next plot is, okay, what's the intensity? What's the values of these points at different places? So it's nice to be able to see where they're at, but you also want to see how they correlate to the other points around them, right? You know, and using that Bouguer anomaly value, which is what I ended up doing, I created a bubble plot showing the intensity given the size and also the color. So kind of jump out a little bit more, that you can pretty easily see that on the sort of the eastern side of this thing, you have higher Bouguer anomaly values than you do on near the edges in the other directions. And then saving that as well. And I guess I did include a lat long version of everything as well. So again, it was, you know, for the masses, that's what I was thinking of a few days ago when I was asked to do this. I wanted to make sure that there was enough stuff here that everybody could maybe find something useful for their own research. But that's what I have right now.
Awesome. Thanks, Troy. That's
Mhm.
cool. So what is the bottom line? Why do you have those big gravity values associated with the butte?
The bottom line is there's some type of dense intrusive feature coming up through. Looking at the bubble plot, I mean, it can reveal maybe a little bit about the geometry of the body, but it's either thicker here or closer to the surface here. Or it's more dense and thicker in this area. And then it seems to drop off really quickly on the northwest and western edges, and it seems to still be captured a little bit further down in this way. So like if I were to go back out, I would like to get more samples in some of these dead spaces to try to get a better handle on the geometry underneath the butte.
Sorry, which area is that, and what's butte?
Oh, it's Table Butte. It's
Is it
north.
Blackfoot?
It's northeast of like the INL, the Idaho National Lab. It's the northeast near Mud Lake, just north
Oh,
of Mud
okay.
Lake.
I've never been there. Okay.
In the eastern Snake River Plain.
Yeah.
And what is supposed to be?
Well, that's the thing, is it's kind of hasn't really been thoroughly researched, and there's only like another real theory on this, is that there was a phreatomagmatic eruption that then turned into a dry eruption that built up this butte. The weird thing about this butte is it's huge. It's 7.5 kilometers east-west and about 6.5 kilometers to the north-south, and it only has about 100 meters of relief on it. So compared to a lot of the other buttes that you see in the eastern Snake River Plain, it's large. It's got a larger footprint, but it doesn't have the kind of topographic relief that you would think of with the other buttes that you see.
Yes,
So
it's a low aspect ratio feature.
Yeah. So the idea is there may be a silicic or basaltic body under there that just barely came up close to the shallow surface, and it's sort of just pushing it up. Right.
Okay.
So
It doesn't have any crater or anything, right?
there are vents along the top. There's actually a series of vents. There's one of the articles that was written on it does go into pretty good detail about the vents that have been assessed and put into a catalog. And there's also some dispute on what is a vent and what isn't a vent. So is it rootless? Does it have and that's the idea, is this gravity survey and the magnetic survey will help to sort of explain some of those, especially even the vents. You know, if we decide that we need to do more detailed mag surveys or gravity surveys, we could easily figure that out and then say, okay, yeah, this one's a vent or that one's not. Right now, a lot of that work's been done pretty much using remote sensing techniques. So, and there has been some field work out there. It hasn't been extremely extensive though. So we're hoping to answer some of
Do we
those
have an idea of
questions.
do we have an idea of what the butte is composed of? I mean, is it like volcanic products? And it's like,
Yeah, the upper surface, it's got like at least from what I've been able to tell, there's about 20-meter thick packages of basalt on the top of it, maybe a
okay.
little bit more than that. But what's underneath it it doesn't have a lot of exposure on the edges either, because what you see on the edges is actually basalt. And there's been no drilling in that area, at least on the butte itself. And there's not much exposure at depth, because there's only like maybe a few small gullies that you can maybe see lower down into the units. And even at that, what they're seeing is basalt. So when they went through, one of the studies had, I think they decided on 4 different units based on variation in composition. But that was, minor crystallinity differences and things like that. They all pretty much, if you look at the diagram where they have them, they're basically in a circle. I mean, they're all really close to each other. So there's definitely different phases that went on, but there's still no real clear-cut answer as to what created it.
It's mapped as a shield,
Okay.
Yes.
and it just isn't. So,
Yeah.
so that's a problem with it. And the basalt units that are mapped on it, don't conform to the circular outline shown here, the topographic high at all. I mean, the basalt lava flows sort of cover the edges and meet in the middle. And it doesn't make any sense for lava flows, right? Because it would kind of imply that they're flowing into each other on top of the butte.
Yeah.
See what I mean? So there's sort of a pretty good indication that it's uplifted, but it's a very weird uplifted shape. I mean, one idea was it might be a tuya.
Oh yeah.
But we talked to a glaciologist, and he said, no, that part of the Eastern Snake River Plain has never been covered by glaciers.
Okay.
So, but it has sort of like a tuya shape to it. So we think it's an uplifted dome. I mean, there are other uplifted endogenous domes in the area, and so it could be that that's what this is. It's very intriguing.
Only basalt. There's no other.
No, there's silicic domes as well. Uplifting basalt. So there's huge domes that are to the southwest of this that are some of the largest domes on Earth, actually. And
no. I was talking about the butte itself. Like, when you do the stratigraphy of the butte,
you only see the basalts and you only see superficial lavas. Although, intriguingly, to the south, there's some phreatomagmatic deposits.
Okay.
And I think I think those are blowouts on the side. They might actually indicate late stage hydrothermal activity, which could have actually accompanied this intrusion. So it's sort of interesting. They're to the south of the main part of the dome.
Yeah, they're down in this area, so on.
Okay.
Yeah.
Called the breaks.
Very, very curious spot. Well, anyway, cool notebook, Troy. And I love the idea of taking that complicated data set and sort of going through step by step. I think it's one of the big advantages of notebooks for processing data and stuff like that. Are there any other questions about that stuff?
Yeah, I have a couple of questions. The first one was, so that phreatomagmatic portion, wouldn't that technically support what you were saying of potentially being a tuya?
Well, the problem with the tuya idea is there's just no glaciation.
Yeah.
So we can't use that mechanism.
Yeah.
But it does support the idea of there being, late stage magmatic activity that, maybe postdates the emplacement of the basalts.
Yeah. Yeah, I was wondering if they were 100% certain on the glaciation portion, or if it just kind of.
Yeah, they seem to be extremely convinced. I mean, that there were, I'm not a glaciologist, but they're basically saying, yeah, all of the mountains obviously had intense alpine glaciation,
but not down
The
in the
Snake
plain,
River
right?
Plain never had a glacier. So, you know, and that actually makes sense looking at some of the other volcanoes. I mean, it's pretty obvious that you know, Pleistocene volcanoes are not ever carved by glaciers or anything like that. So it's pretty clear from a bunch of geomorphology.
Hmm. And
No,
then the other question.
I like the hydrothermal, you know, theory, because I mean, you know, that can be very short-lived, but that can be just a single, you know, event that occurred during the uplift of this structure. So I mean,
Yeah,
if you find a vent related to that, to these deposits, then why not?
right. Well, I mean, the other cool thing is that gravity anomaly that Troy showed, it's 5 milligals, which is just I mean, you know, that's just a giant gravity anomaly for such a small area.
Okay.
So it's definitely a strong density contrast. So Troy, you're going to have to get together with Grant and model the gravity and the deformation. You guys could write a nice paper.
Yep.
That'd be fun.
I think you definitely need a viscoelastic model, because that's some extreme deformation there.
Seriously, yeah.
Yeah, it doesn't work elastically, that's for sure. Anyway, very cool. Hey, Robert. Oh, go ahead, Franco. Did you have another question?
I had one more question for Troy.
Sure.
Any particular reason why you wrote it as different codes of different code blocks? Is there some portions of that can be applied while ignoring other portions of the code, or, you know, is there a functionality for the user to only apply portions of the code that would be independent of the other portions?
To an extent, yeah. Like I basically, so some of more of these visualization codes, the actual like the definitions for the gravity and whatnot for magnetics, I kept those individual just so more for my own sake to be able to see them separately. The visualization codes, like I've said, I've used them in both of those with minor changes. So you're some of these, like I said, more the visualization stuff you can pull out and plop into some other code, and you don't have to do really much anything except for maybe add a new package to when you pull in the libraries. So for this, it's really a walkthrough more so, but I don't. The processing codes themselves more or less go hand in hand. You need one to the other, to the next, to the next to figure those out. The reprojection code is another one where you can run it on anything. It doesn't have to have anything except for a data file fed to it. So some of them yes, some of them no.
I could definitely see somebody using the code blocks that, you know, go through pulling the Google Earth satellite image and making a bubble plot of your data. I mean, that can be used for almost anything, any kind of visualization of geophysical or geochemical data.
Yeah, I was actually thinking the same thing about the bubble plot. Like, I mean, that's something like you were talking there a few weeks ago about gas dispersion and concentrations and stuff. I could see that being used to look at something like that pretty quickly, or even looking at tephra deposits for thicknesses. You can plop them in there, or grain size distribution. You can plop them in there, and it'll show you the how those things are distributed. So some of them, yeah, some of them, no.
Okay, cool. Thank you. And the other thing was, sorry if I missed this piece of information. What was causing the spiking on the first one?
It's instrumentation. So like when you get really close to being in line with the Earth's magnetic field, it drops out. It acts like it's not there. So this problem also exists like near the equator. So it's something that you can't really get rid of, so you have to learn to deal with it. And the way that I dealt with it was by manually taking out those dropouts and only looking at leaving in the spikes that I felt were related to the actual signal itself.
Okay.
So,
Cool.
so you're basing that mostly on the amplitude, right? So you're looking at the minimum and the maximum.
Yeah.
But maybe you should also look at the time, because this spike maybe are just only like very short-lived events, and you don't want to, if you have an anomaly that is the same amplitude as your spike, you don't want to remove that anomaly, right?
Yeah. So if and I'll show you how I did this visually real quick. Back to make sure I'm clicking the right window. So if you look at all of this data, I mean, this is the raw data, but you're looking like this guy here is like, maybe it's a little easier here. So for this one, it's not as bad. It's 8,000. And I got rid of just that point and I kept everything above it. But on some of the ones that I have, and this actually had less dropouts than some of them. And I know what you mean by a time, because I was trying to figure out if this thing was kind of cyclical in some way, and it's not. Some of the lines don't have any of them, and some of the lines do. So it must have been the way that I was moving relative to the Earth's magnetic field. Maybe I bent over, I did something wrong, or not necessarily wrong, just the way that I was positioned. Some of my lines had huge dropouts, like, this one's 8,000. I had some that were even greater than that. Like,
Okay.
so when I look at this and I'm like, okay, I will keep that one, and it's on the end, so it doesn't probably make a huge difference. But this guy might actually like really mess up some of the readings around here. And there's nothing else in that area, like when you zoom into it, or it's hard to zoom in, but there was nothing on either side of it to say that, yeah, that is definitely something. So yeah, that was actually a problem that I have, and I'm still kind of working through it. I got with Rocco and was like, what's probably a good way to attack this? And that's kind of what he does, is he goes through manually and removes points. So I was like, that's what I had actually started doing when I was collecting this data, to try to get rid of them. I know after talking to Chuck, there's also a Fourier transform, which there's some pitfalls to using that as well. And upward continuation was something else he had mentioned. I haven't quite got to writing codes for those yet, but it's definitely something to look into, because quite honestly, this was sort of a pain to go through and visually assess each line to make sure that you're, and I keeping points in there that are artificial, or that need removed, possibly. So that's definitely something I want to work on, is that part of it, and adding in more processing steps as well. Just kind of fine tuning the whole process.
Cool.
Yeah.
Thanks.
Yeah, probably whichever route you decide to go with, as long as you stay consistent, I think that's when it's fine. But
Yeah, and that's
the problem
kind of
with
what.
visually assessing, it's hard to stay consistent for anybody.
No, and that's definitely something when I was talking, when I was trying to figure out ways to attack that, I've always told, and Rocco had mentioned it too, is like, make sure you just explain what you did. You know what I mean? And yeah, there's definitely some improvements that need made, and that's the sort of the next step in the game.
Awesome.
Very cool. Anybody else for Troy or Grant? Robert, are you good to go?
Yeah, can you hear me all right?
Yeah, we can hear you.
All right.
Why don't you show us stuff?
I just want to make a comment about Troy, your code there. I'm going to have to steal that plot with the CartoPy inset. I hadn't thought about doing that. I really like that.
That was Chuck. You can thank Chuck for that, because that's where I got the inspiration.
Was that a desperation?
Yeah, I didn't think about combining CartoPy like that. Can you see my screen?